Okay, so thanks everybody for coming. It's a pleasure and an honor to have James Binney here to give us this mini lecture course on stellar dynamics. Probably many of you know him because of the textbook, Galactic Dynamics, which is the standard textbook in most universities for galactic dynamics. James is a emeritus professor at the University of Oxford, a fellow of the Royal Society, and many other titles and awards during his career. So he kindly agreed to give us this lecture course, which is based on a new book on stellar dynamics that he's writing, and that he kindly made available in PDF format as a draft in advance for this lecture course. So those of you that have subscribed to the course should have received the PDF. If you have not subscribed but you are here and you would like to receive the PDF, just let me know and then we will send it. Okay, thanks, Matthew.
Well, it's a pleasure to be here, and I'm hoping to find this a very useful exercise because you're going to point out all kinds of problems, and you'll perhaps get this thing shaken down and it won't be too embarrassing when I let a wider audience have a look at it. So today I want to this is kind of my agenda of what I hope to cover. Maybe we'll cover more. I don't know, but let's see. So first of all, the scope of the lectures and what I'm trying to do. Something about what makes stellar dynamics its own particular branch of physics, rather different from other branches. One of those is negative heat capacity. I'll talk about negative heat capacity, evaporation, and then begin work on a theme which will keep us busy for the next couple of days of what I call mean field theory, that's equilibrium models, by talking about the isothermal sphere, which is a very interesting equilibrium model in stellar dynamics. And then I'll talk about the Boltzmann and Liouville equations, and which is an exact calculation which gives you insight into how stellar systems evolve. So Galactic Dynamics, the textbook with Scott Tremaine, was planned around 1979. The first edition appeared in 87, and we did a revision in 2008, which wasn't as radical as I think it should have been. We both, Scott Tremaine and I, had very heavy teaching and ministry responsibilities at the time. It was difficult for us to spend time in the same place and so on. So that was a lighter revision than probably it should have been. And in any case, well, obviously an awful lot has happened. It would be terrible. A lot intellectually hasn't happened since 1979. But actually a lot has happened, surprisingly perhaps, in the last decade. So I felt a year ago that a complete fresh start was necessary. I've made this my goal with this book has been to make it self-contained whilst minimizing the overlap with galactic dynamics. I don't want to go over all the same old ground. On the other hand, I don't want readers to be constantly rushing to the library to find a copy of Galactic Dynamics in order to understand some section. But I also wanted to have a very strong emphasis on fluctuations. I feel classical stellar dynamics was very much concerned with equilibria. I mean, it wasn't entirely concerned with equilibria, but a lot of the subject was to do with steady state models. And we need to move forward from that now, partly on account of observations. We now observe our own galaxy and even other people's galaxies through instruments like MUSE in such horrific detail that we can see the disequilibrium. We can see these things quivering and moving around, oscillating around equilibrium, and we have very little. We are very inadequate in our theoretical understanding of this. This isn't a completely new area, but I think the need has become more pressing than ever. Okay, I think I've said that. Right. So this is just, I'm just flashing it, is contents pages of the current draft, and I will be handling sort of, I'm going to try and cover some topics, but obviously not all, in the first 4 or 5 chapters. things that I want to cover that you won't find in textbooks because they weren't around in 1979 are torus mapping, what I call F of J modeling, that's modeling equilibria using distribution functions that depend on the actions J. Van Kampen, so-called Van Kampen modes, which are, as I will be explaining, are actually the modes of stellar systems. People talk about the modes of stellar systems routinely when they don't mean the modes of stellar systems. Almost nobody actually refers to the modes of stellar systems, which are the so-called Van Kampen modes. The things people talk about as modes of stellar systems are things related to Landau's analysis, which are not modes at all. And I will be illustrating this when possible with the periodic cube, which is a theoretical model. It's a toy model, but it's a very tractable toy model, and I think an excellent place in which to experiment, which has been curiously neglected until recently. Okay, so what sets stellar dynamics apart from ordinary condensed matter physics, from ordinary statistical physics? The key thing is the long-range nature of forces, right? And this diagram down here illustrates the situation. The thing is that the stars if we think of the gravitational force on a particle that sits here at the origin, the stars over here in that shaded area pull that particle to the right, and these stars pull the particle to the left. So if the distribution of stars in this zone were homogeneous, or even radial centered on there, the mass here would be the same as the mass there. The forces would cancel. There will be no force. Where does the gravitational force come from? The gravitational force that there is on the sun or whatever, it comes because as you go far in this direction, the density of stars, shall we say, falls off relative to the density in this direction, which maybe increases. And you can see that the imbalance in the forces coming from the right and the left will arise on the scale, will arise from stars which lie at the scale on which the density shifts, the density declines, which in our own galaxy is measured in kiloparsecs, whereas the nearest stars are on the order of a parsec away. So what makes this is completely different from what happens in an ordinary liquid or an ordinary solid, where it's just the near neighbors that impose forces on each particle. Another thing well, because the force is accumulative, because there's no such thing as negative mass causing a repulsion, systems are inherently, you can't allow the system to grow. So in condensed matter physics, the forces come from near neighbors, and you can consider systems which are bigger and bigger and bigger and bigger, the so-called thermodynamic limit. You can't do that in the stellar dynamical case because the stars which are your current outside of the system are the ones which are actually dominating the forces. And so as you change the size of the system, you change the physics of the system. And another point that's highly relevant is that systems are inhomogeneous. They're apart from the periodic cube, which is only a scientific toy, real stellar dynamical systems always have some kind of a middle and some kind of an outside, and the forces, everything is changing on these scales. That is extremely inconvenient from a mathematical point of view. So plasma physics is the nearest thing to what we do. There, the forces, the electrostatic forces come from a fairly large, well, the volume that can be fairly large, the Debye sphere. But the magnetic forces come from much bigger. They are indeed system size. But the key advantage, what makes plasma physics harder is that it's inherently a relativistic problem, i.e. magnetic forces have to be considered. We're going to be doing this in the Newtonian context, in which case we only have the general relativistic analog of electrostatics. So in the plasma case, the forces are more complicated because you have both the B field and the E field, but we do have the simplification that we can consider an infinite homogeneous background plasma because we have positive and negative charges, and so they they on the average cancel out. So on the average, there is no force that can allow the system to grow. Whereas we cannot do that, and you'll see that that drives us mathematically to some unpleasantness. Okay, so some very basic points. Particles move under this Hamiltonian. Well, Hamiltonian I'm going to write like this. So we're going to say that H is a function of x and v, not of x and p, because it's convenient to work with the momentum per unit mass. So this thing v, you should think of as the momentum per unit mass, and this phi, the gravitational potential, of course, is the potential energy per unit mass. So this is the ordinary boring Hamiltonian of quantum mechanics. H is p squared over 2m plus v, the potential energy, where both where we can get rid of, we can divide through by m and get rid of m because the potential energy is proportional to the mass, as is the kinetic energy. And mass will always be occurring in this context multiplied by the Newton's constant g. And of course, we know dimensionally that v squared is gm over r from the characteristic velocity is given by the mass gm divided by the radius. And that has the consequence that if you form a thing like this, a gm times the length L and take the square root, you have something which has the units of angular momentum per unit mass. So momentum is going to be per unit mass, angular momentum is going to be per unit mass. We know from quantum mechanics that h bar has the dimensions of angular momentum. So in a way, this commodity here, which we call the actions, as you'll see, plays a fundamental role in the same way that things like angular momentum, which have h bar for dimensions, doing quantum mechanics. Density is obviously has units of mass over length cubed, and when you consider this speed, you soon find that the unit of time is g rho to the minus a half. So and this happens to be, if you want to think about this physically, it is the time it takes a universe made of density rho and initially started stationary to collapse to a singularity. That's essentially what this time is here, within factors of root pi or something. The gravitational potential energy has units of gm squared over r. Now this is potential energy not per unit mass, but potential energy, hence the squared. And we write it as gm, we define the gravitational radius rg by saying that whatever potential energy is of a system of mass m is this number here. And that could also be written as a half of the mass of a single particle times the gravitational potential in which that single particle exists, the half being there, because if you disassemble the system, to take the first particle out, you have to do work m phi 1. To take the next one out, by the time you take the next one out, phi has got smaller because there are only n minus 1 particles remaining. And so the potential gets smaller and smaller, and that's where this half comes from. And because we know that the potential between point particles is gm squared over x minus x primed, these expressions are common. So what's really important for us is that systems can be rescaled in length or in mass. You've got two free scalings. You have a model, you can map it onto a real thing in the universe by upscaling its mass or upscaling its length scale, or both, as you will. And it is just that the velocities and the time scales will scale up and down according to these rules here, right? So that's a considerable convenience that you've got this high degree of scaling, because gravity doesn't define a natural scale. It's one of the most important results in the elementary theory is the virial theorem. I won't take you through the calculation, but remind you that we calculate, we derive the virial theorem by writing down the equation of motion of one particle under the attraction of a load of other particles, and we multiply this equation by xi. We multiply the acceleration of particle I by the position of particle I. We use this elementary result, this elementary piece of calculus to get rid of, to eliminate that. So now we have two terms on this side, and then we do a little bit of rearranging. We recognize that this is going to give us the kinetic energy, K, and we're also going to have this spare term here that we don't really want. And on the right-hand side, we've got an X into this, and then we rearrange this because we argue that we're summing over I and J. We would get the same, because we're summing over an I and J, we get exactly the same thing if we change that to an I and that to a J and that to an I and that to a J. We swapped the indices, it would come to the same thing. So let's swap the indices and write and add it in. So this is the original thing. This is the thing with the indices swapped, and there's a half out front to compensate. And now we can combine these two things, and then the xi minus xj mod squared cancels top and bottom, and we find that this is exactly the potential energy, the gravitational potential energy. So we arrive at the conclusion that twice the kinetic energy plus the potential energy is equal to this acceleration of the moment of inertia. And then we argue that if the system is in equilibrium, more or less, sort of growing or shrinking, then this moment of inertia is not doing anything very much. It's just going to be about equal to a constant, a fluctuating constant. And so we can identify this with a large number of particles as being zero. And then we have the crucial result that twice the kinetic energy plus the potential energy is absolutely nothing. Said another way, of course, it says that the potential energy is minus twice the kinetic energy. And that gives rise to a really important property of stellar systems, namely they have negative heat capacity, because if obviously the total energy in thermodynamics, often called U, is equal to kinetic plus potential, then we have that the potential energy we've discovered is minus twice the kinetic energy. It follows that U is minus the kinetic energy. And the heat capacity is the derivative of the internal energy with respect to temperature. And if I say, and given the conclusion that U is this, then I have that the heat capacity is minus the derivative of the kinetic energy with respect to temperature. But for a monatomic gas, so if you're thinking about a star cluster, you should be thinking about a monatomic gas. The kinetic energy is 3/2 Boltzmann constant times the temperature. So we've arrived at the conclusion that the specific heat is minus 3/2 of Boltzmann's constant, negative specific heat. Now, if I take a system with positive specific heat C2, and I put it into thermal contact with one which has a negative specific heat C1, something interesting will happen. Initially, they're at the same temperature, but if an amount of heat dq flows from 1 to 2, then both systems get hotter. One gets hotter because it has negative specific heat, and I took heat out, so the temperature went up. And of course, 2 gets hotter because it has positive specific heat and it absorbed heat. We find that the first system goes to T1 primed, which is the original temperature plus the amount of heat that transferred out of it, divided by the modulus of its specific heat. Whereas T2 gets hotter by the amount of heat that it acquired, divided by the modulus of its specific heat, which is actually its specific heat is positive. And when the systems are in when two systems, ordinary systems, are in thermal equilibrium, if heat comes out of one, the one that gains the heat gets hotter than the other one, and heat flows always from the hotter to the cooler. So since the one that absorbed the heat ordinarily is now hotter, any fluctuation of heat towards one system will be reversed. The thermal conductivity will push the heat back, and the system will be stable. So the condition for stability, namely that the second system, having absorbed the heat, is hotter than the first system which sent the heat, is this condition, which is also this condition. In other words, the system with positive specific heat that you put in contact with a stellar system which inherently has negative specific heat is going to be, this relationship is going to be stable only if the positive specific heat system is relatively small. you cannot, in particular, you cannot do what people do in thermodynamics, which is put your system in contact with a heat bath system of infinite, very large heat. If you did that, your stellar system would transfer heat to the heat bath. It would get hotter, and the heat bath barely would because it has a huge specific heat. And so now there'll be a temperature difference driving heat out of your stellar system into the heat bath, and you'd have a runaway. So we'll talk about that. I mean, that we'll develop that idea a little bit later. So it's crucial that stellar systems can be in contact only with relatively small heat baths which in some sense have less heat capacity in an absolute sense themselves. Evaporation is a very important phenomenon when you're thinking about star clusters. The escape velocity associated with the gravitational potential, we all know, is this square root, right? The gravitational potential is negative, so I need a minus sign for taking the square root. But we have with a half mv escape squared is equal to m5. So the energy, the gravitational energy of the system, which we already agreed was a half of m phi I, then when I replace phi I with the appropriate escape velocity, I come to the conclusion that the gravitational energy of a system is always minus a quarter of mass times the sum of the squares of the escape velocities of the individual stars, because the escape velocities are simply a measure of the potential at the location of that star. The kinetic energy, we've agreed already, is half mvi squared. And by the virial theorem, we know that this is minus a half of that. So putting that condition in and cancelling this and that, we discover that the sum of the squares of the escape velocities is simply four times, is simply 4 times the mean square velocity of the system. So what is that telling you? That's telling you that the escape velocities are actually not that much above the actual velocities. Now, in an ordinary, we in thermodynamics, system mechanics, we reckon we understand that the encounters when particles exchange energy in a random kind of way, by encountering each other, or in a random way, it doesn't matter how, they tend to establish a Maxwellian distribution of velocities. Now, a Maxwellian distribution of velocities, it's easy to work out from this integral here, has a fraction about, which is essentially 1 over 135, 100 level. If I take a population of Maxwellian of particles which have a Maxwellian velocity distribution, 1 in 135 of those particles is moving faster than twice the RMS velocity, because that's what this says. It says V escape, well, the typical V escape, the RMS V escape is twice the RMS random velocity. And if you work out what that means for Maxwellian, it means that if you start with a Maxwellian distribution and ask who's got a velocity above their escape velocity, the answer is 1 particle in 135. So what does that mean? That means that the star cluster is going to evaporate. Evaporation is precisely evaporation out of a droplet of water is very precisely the same thing. It's a molecule of water which is going sufficiently faster than the average that it is able to escape the potential barrier associated with surface tension and push off. So in the first crossing time, 1 over 135 particles goes, taking with it, of course, more than the average, more than its fair share of energy, and therefore reducing the energy of those who are left. That's evaporative cooling. Once they're gone, you have to wait about a relaxation time for the encounters, for the fluctuations and the potential to repopulate the tail of Maxwellian. And now there will be another particle in 135 that will push off. So every relaxation time, that tail will get repopulated, or the system will attempt to repopulate that tail, but the particles it puts in there will push off. So after about 135 relaxation times, the whole cluster will evaporate. That's in round numbers. There are globular clusters, on the other hand, are amongst the oldest objects in the universe, right? Now, when I was a graduate student, globular clusters were demonstrably older than the universe. It was one of the problems that with which people wrestled. So it makes you think. Well, it tells you really that these clusters, they are about 100 relaxation times old, central relaxation times. So evaporation has been significant, but it hasn't wiped them out. But of course, that's the definition. The globular cluster that we see of ones that weren't wiped out. There were smaller clusters in which this process happens faster, which of course are not there, therefore we don't see them. Okay, now a key result with absolute elementary physics is that if you work out the rate of change of energy of a particle which is orbiting in a gravitational potential phi, you're looking at this derivative, and you take a derivative of this, and you get something to do with the equation of motion. You take a derivative of this. This depends on time and space. And so when I take this total derivative, I need to include both the time derivative and the space derivative. And the space derivative cancels on through the equation of motion on the time derivative of this, and we're left only with the time derivative of the potential. This equation is telling you something really important. It's telling you that the energies of individual stars change if and only if the gravitational potential in which they move is fluctuating. And so we are very much interested in the rates of change of the energies or the orbital properties of stars. And this is telling us that we can inquire into that only to the extent to which we get to understand the magnitude of this thing on the right-hand side. What is it that provides this? Well, if you disturb a stellar system, you can do, people learn about this basically by building n-body models. If you disturb a stellar system, it wobbles a bit and the wobbling dies away. We will discuss why the wobbling dies away further down the line, but it does. And so during that wobbling phase, there is the possibility for stars to change their energies, and you might say approach some kind of statistical equilibrium. And that is what Lynden-Bell called violent relaxation. It's relaxation in the sense of a shuffling of energy and whatnot between stars, and it's violent in the sense that it's organized. It's organized fluctuations of the whole system that does it. The later evolution, after the system has settled down, is driven by much smaller fluctuations, for example, associated with Poisson noise, and we will talk about that. So now we come to the fundamental ideological structure of stellar dynamics, which was appreciated already at the time of the First World War when Jeans and Eddington founded the subject, which is that it breaks into two parts. First, you say, let's ignore fluctuations. Let's imagine that the gravitational potential is constant, that stars move in some kind of average, smooth potential that is created by all the stars together. And that's what we call mean field theory. So that we're going to ignore small scale structure and fluctuations. We're going to focus on the larger scales because we know gravitational forces are generated on large scales and not sensitive to what's happening on small scales. And we will come back later to talk about how fluctuations, such fluctuations as arise, cause the system to evolve from one mean field model to another mean field model. This is not so different from what one does routinely in condensed matter physics, where again you have there is a subject mean field theory which ignores fluctuations, and then you know there's a big apparatus associated with the theory, for example, of critical phenomena, where you struggle to understand what fluctuations, which can be when they're large, do to you. Okay, so we're going to work extensively with the one-particle distribution function, which I will interpret in the following way. That f of w, that's the distribution function, w is going to be a six-dimensional object. It's going to contain broadly speaking, the positions and momenta of an individual star. So that's going to be a unit of phase space volume d6w. So this is going to be interpreted as the probability that any given star can be found in that volume around that location in phase space. We're going to consider our stars all to be equivalent. Stars, of course, are not equivalent, but you're entitled to operate at some level where you treat them as equivalent. And so, since this is a probability density, it follows that if you integrate it over all phase space, you get 1. Must be normalized in that way. And the actual density rho in kilograms per cubic meter is going to be the mass of the entire system times this integral over velocity. Right? So let's talk about the isothermal sphere as the simplest possible, and that fiducial mean field model. So, and we know that this, from statistical mechanics, this system has a certain special legitimacy, because we know from undergraduate statistical mechanics courses that this distribution function, the probability density being e to the minus beta in inverse temperature, which appears first as the Lagrange multiplier, times the Hamiltonian, this distribution function maximizes the entropy given subject to a given energy budget, right? And we know that from statistical mechanics that you get excellent predictions for the macroscopic properties of things if you assume that their probability densities are maximize the entropy subject to a definite amount of energy. This was something which was for Gibbs in 1900, an empirical fact, and it was essentially explained by Shannon in 1947 or 48, who understood that entropy was the unique measure of what a probability distribution does not tell you about the subject you're trying to study. So you're maximizing the uncertainty in your probability distribution subject to what you know about it, which is alleged to be what the stock of energy is. Okay, so let's study this system. The density at x is going to be the integral of the distribution function over velocity, and this is an integral we can do, right? I mean, the nice structure of the exponential allows me to take the e to the minus beta phi spatial part out of the integral, do this integral, which is elementary, and we end up with the conclusion that the density is proportional to e to the minus beta times the potential. We don't yet know what the potential is, so that we're not yet there. But we argue that the system has to be spherically symmetric because there's nothing which gives us a sense of direction. So the density will be a function of radius only, and therefore the density from this can be written as the density at the center times e to the minus beta times psi, where psi is simply the actual gravitational potential minus the gravitational potential at the center of the system, so that when I put psi equal to 0, that becomes 1, and we find that rho of 0 is rho of 0, which is what it should be. And now, to find what the structure of the system is, what rho and psi of radius are, we solve these couple differential equations. This says the rate of change of mass is 4 pi r squared times the density at radius r, which we've already established is given by this. And this says that the rate of change of the potential is the gravitational force provided by the mass inside radius r, because Newton already told us that that's the way spherical systems work. So these are two very straightforward equations to solve on your computer with Python or whatever. And if you solve them subject to, you just you choose row 0 so that G row 0 is 1, some arbitrary normalization, not a tiny bit of interest, and you say that the mass at some very small radius is given to by 4/3 pi that radius cubed times the central density. In other words, you assume that in the middle the density is constant, nearly constant, so mass rises like the cube radius. Then you'll find that your solution looks like this. It's flat. But when we get to a radius of about 1, it begins to fall. It falls quite steeply, and then it slackens off, and asymptotically it falls like r to the -2. Now, from this one solution, we can now make a whole zoo. We can now make a whole zoo of slow dynamical models using the scaling that I mentioned earlier. So if you take the model up to here, this small radius, and rescale it so that this small radius becomes some standard radius, we'll call it R0. You rescale it in length, and then you rescale it in mass back to standard issue mass m. You have a complete solution. You'll know what the density is everywhere. It'll be nearly homogeneous, but not quite. And you will know what the random velocity is everywhere, because, as we will discuss in a minute, the inverse temperature scales. The inverse temperature beta is more or less 1 over v squared, 1 over the characteristic velocity, right? So we know how it scales. Or we can take the solution up to here, say up to 1, or some similar thing, and we can rescale the solution in here so that this radius becomes R0, and this larger mass that we've got trapped, we'll have to rescale in mass by a smaller amount up to our standard issue mass m, and we will have another model. So we'll be able to develop a whole sequence by changing the radius up to which I take the solution. I will be able to construct a whole series of models, all of which represent a mass m of gas trapped within a sphere of radius r. And these gases are going to differ in their temperatures. The very first one we constructed will be almost homogeneous, like the air in this room, because the temperature is so high that gravity doesn't get a grip on the gas. The particles are moving too fast to be deflected by the gravitational field. So that will be confined by the walls of my sphere at radius r and will generate a good pressure. The model that I get by going out here will be that same mass of gas in that same sphere, but at a lower temperature, where the particles are moving, are not moving so fast, so many of them are deflected by the gravitational field, never make it to the walls, and the pressure in the walls will be smaller. So that's what happens here. Here we see how the temperature rescales, right? So m of R0. I'm taking my sphere. And my solution I showed you on the other slide, and I'm cutting it at radius R0. And then I'm rescaling R0 until it becomes big R0. Same thing over here. In a little contemplation, you'll conclude that this is how the gravitational potential scales, and this is how the inverse temperature scales. Now I can compute the internal energy of my system, of all of these objects. The internal energy of my system is going to be the mass that I've got times the inverse and the inverse temperature, and this is going to be the the potential energy. So what happens when you do that? So this is okay, and the parameter we're going to use to describe these objects. I've got a 1-parameter family of isothermal spheres. They're all sitting inside a sphere of radius big R0. They all have a mass of big M0. And the density at the center, as we go down this sequence to lower and lower temperatures, higher and higher inverse temperatures, the ratio between the density at the middle to the density at the outside where it touches the sphere is going to become bigger and bigger. So that's what's plotted along here. This is the, on a logarithmic scale, is the ratio C of the density in the middle to the density at the outside of this ball of gas trapped inside my sphere of radius R0. And this is the inverse temperature. So right here where this ratio is 1 is a gas like the gas in this room for which its self-gravity is unequal. So and as I move up here, beta is increasing, so the temperature is decreasing. And eventually, when I get to as the temperature decreases, this ratio increases because gravity is doing more and more work confining the gas. Right, and when I come to some point here, when this ratio is about 38, the inverse temperature becomes constant. What does that mean? That means that to proceed further, so as I was drawing heat out of the system, and the system was getting cooler, like any ordinary boring gas. Once I pass this point, as I draw heat out of the system, the temperature is rising. Why? Because the system has become one of negative specific heat. What does the internal energy do? Sorry, I've lost the label here. This is the internal energy. As I cool the system, the internal energy drops. Surprise, surprise. When I come to here, which is at a density contrast of about 6, the internal energy passes through 0. Now, the potential energy is exactly minus the kinetic energy. Keep cooling, and we pass through this point where the specific heat turns negative without noticing anything. And I come to this interesting point here, where the density contrast is 708, when the energy bottoms out. So all the way along here, I've moved my sphere to greater and greater central density contrast by drawing heat out. In order to follow these solutions further, I have to increase the energy. So in order to get it more inhomogeneous, according to this maths, I have to put heat in. And that somehow won't make it hotter because the density contrast will be in the middle. We're not going to go back. We're somehow, at this point, it's not making, beyond this point, nothing makes sense. What's happened? What's happened is that beyond this point where the density contrast is 708, or something, the entropy is not maximized by the isothermal solution. So that this distribution function, oh, well, we've lost it, it was on the previous slide, the familiar e to the minus beta times the Hamiltonian isn't the correct distribution function anymore. And a model derived on the basis of it is meaningless. That's sort of illustrated. I mean, here is the entropy. So I can calculate the change in entropy from one state to another easily. It's simply the change in the internal energy, because that's the heat I took out, times beta, because ds is dq upon t. So beta is 1 upon t, and we've just seen, well, sorry, this is a plot of u versus beta here. So as we come down here, we're drawing heat out, we're sucking entropy out. That's fine. But when we get to this point of 708, if we draw any more heat out and follow the solutions any further, the entropy starts to increase because we're having to put the heat back in. It's not making any sense. What actually happens there is the so-called gravithermal catastrophe. So we talked about a moment when C, this density contrast, was about 38, when the specific heat turned negative. that was here. As we progress, we get to a point where the middle of the system, just the middle, is forming a body of negative specific heat. And it's surrounded by a halo, because we're getting this core halo structure, right? It's surrounded by a halo of particles which are behaving pretty much like a system. Self-gravity is not so important for them. It's behaving pretty much like a system with positive specific heat. So as we've gone down this chain of models, and the density contrast between the middle and the outside has grown more and more, we've progressed to a situation where we can split the system into two halves, an inner part of negative specific heat and an outer halo of positive specific heat. And this outer halo of positive specific heat has been getting bigger and bigger, more and more massive. More and more of the mass of our sphere has come, the core's got smaller physically and in mass, and the halo has got bigger, not physically, because everyone's trapped inside the sphere of radius r0, but spiritually. And at this point, the positive specific heat halo has a thermal capacity which is in modulus as big as that of the negative specific heat core, and we've got this instability. So now, what happens in the real world if you constructed, you went to the space station or somewhere and you constructed this, you would find that the thermal that there will be, because these two systems, the core and the halo, are in thermal contact, heat will transfer from the shrinking core to the halo, and the core will shrink and the halo will grow without your doing anything. And the pressure on the walls will rise without you doing anything. There's a lovely paper by Lyndon Bell and Wood a long time ago, which describes the panic in the laboratory when they were conducting this experiment, when this condition was reached. There was a proposal to relieve pressure on the sphere by expanding it. The closer analysis showed that would really make the situations worse. If you want to bring this situation of having a pressure vessel in your laboratory, which is in which the pressure is rising and rising and rising, if you want to bring that under control, there's only one solution. You've got to forcibly squeeze it down, raising the temperature and getting the sphere back below a density contrast of 708. Otherwise, you're doomed. So, gravity and statistical mechanics make for an interesting mix. I hope I've conveyed that. And we now, is it okay to go on? I'm not sure about timing.
Sure. You have another hour.
I have another hour. Right. Okay. I hope the audience has another hour patience. All right. So I'm now about to launch into a slightly detailed calculation, a very classical calculation, but I'll only sketch it. But anyway, we're going to be making extensive use of Poisson brackets. Probably most of you have seen this in some classical mechanics course, but let's just remind you how of it, because I will be using throughout the lectures Poisson brackets from now on in. So a Poisson bracket is an antisymmetric object differential operator made out of f and g. F and g are just two functions of phase space, so they're functions of q and p, position and momentum, and it's defined to be this: a sum over dimensions of df by dqi times dg by dpi minus in the reverse order. And there are many wonderful things you can do with Poisson brackets, but one of the wonderful things you can do, well, one of the least wonderful things you can do with Poisson brackets is write Hamilton's equations that dB/dt of q, the rate of change of q, everybody knows is the partial derivative of h with respect to p, which is also this q comma h, because if you expand the Poisson bracket, this is dB/dq of q, 1 times dB/dp of h. That's what it's supposed to be, minus nothing. And similarly, dp by dt, which is minus dh by dq, can be written as p comma h, because the first term in the Poisson bracket now vanishes, because dp by dq is obviously nothing, and then we have minus dp by dp, which is 1 times dh by q. Okay, so let's do an exact calculation on a globular cluster. We have n stars. It doesn't matter how many. We have n point particles, and they are moving under their mutual gravitational attraction. We do not know the precise coordinates of all these n things. So we work with a distribution function, the n particle distribution function, which is a function of all n phase space coordinates. So again, W stands for Q and P, or X and P. So we've got a function of n phase space coordinates, which when multiplied by the tiny volumes associated around each phase space coordinate gives us the probability of the particle of the system's configuration lying in this volume. And the equations of motion of the phase space coordinates are Hamilton's equations, where the Hamiltonian is the sum of the kinetic energies here minus the gravitational interaction thingy, right? This is summed over all pairs. We're summing over all I except j, and then sticking in a half to deal with the double counting problem. But this thing is the same thing if I swap I and j. And this probability fluid that's described, or the probability fluid that is described by this, has to satisfy a continuity equation, the 6n dimensional analog of this 3-dimensional thing. So f is going to be replaced by this. This gradient operator is going to be replaced by this thing, the derivatives with respect to position, comma, the derivatives with respect to momentum. And then we're going to have rho times the rate of change of position. So rho is going to map to Fn, and the rate of change of position is going to be Q. This is Q dot, and that's P dot, right, from Hamilton's equations. So this is a rewriting of this familiar mass conservation equation. This is a probability conservation equation. When we use this differential operator on this product, we have df by dx times dh by dp plus the hf standing alone and d2h by dq dp. But that term gets cancelled when we use this thing on this thing. And so what we end up with is the Poisson bracket. This is the Poisson bracket of Fn on H. So that is Liouville's. This of course is called Liouville's equation. It describes the evolution of the n particle distribution function. Yeah, and this minus sign means that H has to come first and L come last, right? So that's the evolution equation. So that exactly describes how the probability fluid will evolve if I have these n particles moving under their mutual gravitational interaction. So the question you obviously are asking yourself is, what's the connection between the n particle distribution and the one particle distribution function that I talked about apropos of the isothermal sphere? Well, the answer is that F1, that's what I was talking about before, depends on only one argument, because it's this thing marginalized over all the other locations. This is the probability of finding the first particle here, regardless of where all the other particles are. So I can get the equation of motion of this beastie by integrating the equation of motion for the whole thing, Fn, that we just derived, integrating it over the locations of all the other particles. Now, when we do that, we're going to have integrals like this. We're going to be integrating over any one of these w's. So d6wy is d cubed xi d cubed pi. We're going to have the derivative. We're going to be integrating a Poisson bracket. This is going to involve derivative with respect to x of f, derivative with respect to h of p. And when we when we do these integrals, we can use the divergence theorem to wipe this out, because I can say, yes, I can say the dH by dP, because h is p squared over 2m, I can say that this derivative is simply p, and now I can integrate by parts. So I can move this differential operator by integration by parts onto there. The surface term is all evaluated at infinite spatial location, and where f is presumed to vanish, because there are no stars at infinity. So I'm free to move this differential operator onto there, when of course it vanishes because p is in x. And similarly, we have the same result with these two things swapped over. And because the gravitational force here is independent of p, when I move this differential operator by partial integration onto that, wipes out. So these terms all go away. So the only term in the sum is the Poisson bracket brings with it a sum, and the only term that survives is the term in which I equals 1, where we will not be doing this integral, right? We're doing an integral here over all the w's except 1. So the only term that survives in the Poisson bracket sum is the one in which I is equal to 1. And that term that survives is this. Right? So this is just one term out of the Poisson bracket, and we have to integrate with respect to everything else. And again, we're just putting in the equations of motion, and then we choose to write this as this bit is going to beget that, and then this is that. That's just a bit of notation. Here is that, and now if we define the two-particle distribution function to be the n-particle distribution function integrated over everybody except the jth coordinate, right? That's what that hat means. Leave out the jth coordinate. If I do that, then I can write this thing here as this. So basically, the integral, all but one of these integrals, all but the jth one, has been stashed into the two-particle distribution function. Otherwise, nothing interesting has happened. I've gone from here to here by stashing most of the integrals into here. Now we break the two-particle distribution function we've just chosen. Now, what is this? It's the probability of finding the jth particle at wj, given that the first particle is at w1. And we argue that that is not predominantly, that consists of the probability. No, actually, sorry, this isn't quite right. This is the probability of finding the first particle at w1, more or less, and the second part and the jth particle at wj. That is almost the product of finding the first particle at w1 times the probability, having done that, of finding the jth particle at wj. It's not quite equal to this because this treats these two occurrences as statistically independent of each other. So we add on this bit, which represents the correlation between w1 and wj. This represents how much more likely it is to find the jth particle at wj, given that we know that the first particle is at w1, than just as if it was random. This is the bit that arises because the jth particle actually knows that the first particle is at w1. Now, so we split this and stuff it into the expression we have over the page, and then we get two bits. The bits that involves just two copies of F1 and the bit that involves G. The two copies of F1, we soon discover comes to this, and we move it to the other side of the equation. And here is the other bit. So the potential, so 5x1 is just this. It's a sum over all the other particles of the contributions to the potential at x1 provided by the other particles. And it's simple algebra to conclude that that's what this can be stashed away as that. And so our equation is now looking like this. That the rate of change of F1 when you ride along with x1, with W1 rather. So that is the derivative with respect to the explicit derivative with respect to time plus the derivative with respect to place times the rate of change of place plus the derivative with respect to velocity times the rate of change of velocity, which is minus d phi by dx. So this total derivative is equal to what's conventionally called the collision integral, where our expression for the collision integral is this. So that is an equation. That is an equation for the one part of the distribution function in terms of an integral over the two-particle correlation function. And it's an exact calculation, no approximations. And it's telling us something important. It's telling us that any change that we observe here, any evolution in the one particle distribution function, is driven by particle-particle interactions. It's not helpful in the sense that I don't know what G is, right? But I can't actually evaluate this at the moment because I don't know what G is. Much of what we're going to be doing is arriving at approximations for G. So we need now to get hold of G. The naive thing to do to get hold of G is to go back to the n-particle evolution equation, the Liouville equation, and integrate it with respect to all but two coordinates. Integrate it over W3, W4, W5, etc. But leave out W1 and W2. Oh, that's a nice thought. Thank you. That will give us an equation of motion of G in terms of the three-particle correlation function. And to get that, we'll do the same thing in principle. Integrating out all but three coordinates, which will give me an evolution equation for the three-particle distribution function in terms of the four-particle, and this is the problem. So the naive approach to this problem isn't helpful, and we'll be attacking this problem from various angles because we do want to know about this. We actually observe the evolution of this. Gaia and its predecessors actually observes this thing over here in some detail. So this is a material question. I think this says pretty much what there is a little piece of physical interpretation here you buy online. I don't think I anticipate time for swearing it. Yeah, okay. So this bottom line is kind of okay, all right, yes, this is why I'm doing this. So if all the particles are the same, then this collision term, quote unquote collision term, classical physics is notation that really, is n-1, because that's the number of other particles there are. There are n-1 of these terms, times the rate of change with respect to momentum of this object here, where big F is by definition this gradient. Well, what's that? That is the force at x1 provided by a particle at x2. That's exactly what that is. So this is an integral over all possible locations of neighbors of the force that they provide, weighted by, in some sense, the probability that there is a particle at W1. Well, there is a particle at x1, which involves an integral over the momentum associated with this, right? So this is a density. It's an excess density of neighbors. It's not the density of neighbors because that's dominated by by the F1 times F1. I mean, that's just F1. It's the excess of neighbors because I'm here. So that leads us to the really important idea that what's driving the relaxation is that around each particle, around each star, there is a little entourage. These are contours. Here I am. This is what we've chosen to call X1. And surrounding it, there is an enhanced probability of finding another particle at X prime. And the evolution of the distribution function at this location is given by a derivative with respect to momentum, my momentum here, of the gravitational force on me coming from this excess number of particles around me. So this is what we having to do with ships, I suppose, is called a wake. This is this entourage. And in the language of quantum field theory, the idea is that particles have more than their bare mass. Because they're surrounded by this entourage, this entourage makes them seem more massive than they are. In a disk, in a cool stellar disk like the one the sun lives in, it turns out that this entourage contains on the order of, in excess of, I think, of 100 times the mass of the sun. These are not particles bound to the sun. They come through and they wander off, but they're replaced statistically by some other particle that comes through and wanders off. But if you take a simulation of a disk and allow it to relax, and then you photograph this simulation n times, putting each star in turn in the middle of your camera field of view, and then you stack those images, you can actually see this enhancement. So Toomey and Kalnice did this about 1989 or something. You can actually see this excess of stars around each star. So relaxation. So what do we learn? What we learn from this BBGKY calculation is that relaxation arises because stars are correlated. It would go away if they weren't correlated. This correlation takes the form, or can be thought of as a sort of dressing of mass, which makes stars individually more massive, makes them seem more massive than they are. In a plasma, it works exactly the other way around. Each positive charge is surrounded by an enhanced density, above average density of electrons, cancelling its charge. So when you're outside, the distance associated with this cancelling operation with Debye sphere, there's effectively no electrostatic attraction of an ion. It's all cancelled by the excess of electrons. In a gravitating system, it doesn't work like that. Each star is surrounded by other stars. The other stars add to its mass, they subtract from its charge, and there you go. So that was the end of my overview talk. And do we go the rest, or do I plunge straight into the beginning of the next? I mean, I got massively more material than I'm going to get through this week. So it's a question of what we would like to do.
As you prefer, we can stop or have a break or continue tomorrow or have questions.
Okay, we've got options. Let's do it democratically.
So maybe start with questions.
Do we have some questions, or do we stop for a break and you ask me informally, or do I plunge straight on? We've got half an hour. Is that right?
Yeah, it's about right.
Who votes for stop? Who votes for questions? Who votes for straight on? Right. Okay. You people got more stamina than me. I mean, what I mean is when I'm in the audience. All right, so here's my agenda. I'm going to talk about constant motions, very fundamental idea. Angulation coordinates, absolutely fundamental. Hamilton-Jacobi equation you've probably already seen. Torus mapping you won't have seen, and I want to spend some time on it and use it really to press on to perturbation theory. So my big pitch is that physics in every other area than stellar dynamics is about perturbation theory, right? What's an electron? It's an excitation of the Dirac field. It's a perturbative object. What's a phonon? A perturbative object, right? If you do celestial mechanics, you talk about you oscillating orbits and stuff. It's all perturbation theory, perturbation theory. Stellar dynamics to date has been rather little influenced by perturbation theory. I think the consequences of poor progress. Well, we'll see. This is my pitch. You tell me whether you buy it. So, I think one of the things which has made perturbation theory difficult in stellar dynamics has been the absence of appropriate Hamiltonians for perturb, right? In quantum mechanics, we all know perfectly well that we proceed by identifying suitable Hamiltonian and then perturbing with that thing. And which Hamiltonians do we perturb? It's basically two. Kepler problem, that's atomic structure. And the simple harmonic oscillator, that's everything else. Physicists are not that bright. And it's the same in stellar dynamics. Actually, it's a little bit better. We have slightly more Hamiltonians we can solve exactly the level perturb. But using those, I'm hoping to persuade you that using those, you could do something that's dramatically better, and that's with torus mapping. And that's going to enable us to see some really remarkably, I'm blown away by the beauty of some of the results you can get with perturbation theory when you sit upon torus mapping. That's kind of what I'm going to emphasize. This is the complete agenda from the relevant chapter, and I don't think we will cover it. Okay, but we won't make any progress at all if we don't talk about constants of the motion. So what is a constant of the motion? People probably already know, but it's a function on phase space which commutes with the Hamiltonian. Because it commutes with the Hamiltonian, its time derivative is nothing. So by commutes, of course, I mean that it's Poisson bracket with the Hamiltonian 0. I would remind you that P.M. Dirac always talked about commutators in Hamiltonian in quantum mechanics as PVs. It was by which he meant Poisson brackets. I don't know if you read. Dirac was a famously private and non-communicative person, but somewhere or other, he gave an account of having been heard Heisenberg talking about commutation relations, giving a seminar in 1924 or something when Dirac was a graduate student, and Heisenberg was passing through Cambridge, and that was on a Friday, and he's thinking about it, and then he thought, are these things somewhat familiar to Poisson brackets? Then what's a Poisson bracket? And he was in a torment all weekend because the library was closed and we couldn't find out what a Poisson bracket was. The rest is history. Okay, so if something has vanishing because, and I already derived this essentially in the context of the one particle distribution or the distribution function, if the rate of change of something is always either equal to the Hamiltonian comma something or something comma the Hamiltonian, it's sometimes in this order, sometimes in that order, depending. But if this Poisson bracket vanishes, then that thing is conserved, right? And the standard, so these these constants of motion are at the core of classical mechanics, as it should be taught, but not as it is taught, right? Matthew and I were discussing this at lunch today, that here, apparently, as in Oxford, Newton's influence on mechanics is still far too large. I don't wish to run down Newton just because he came from Cambridge, but because there has been progress in the field, shall we say, in the 19th century. For example, by Poisson, yeah, by mechanics, various people. And if you taught classical mechanics properly, you would start pretty much with constants of the motion, because when you have a complicated problem in dynamics, that's always what you should hone in on, and we don't teach our undergraduates to do that in our first courses, as we should. Anyway, right. So, and the standard route to constants of motion is Noether's theorem. And I always think it's just amazing that any Noether was around in the beginning of the 20th century. No, she wasn't around the beginning of the 18th century or the 19th century. I think. Anyway, they did. I won't bore you by telling you again what Noether's theorem is, but probably we are all aware that conservation momentum arises because it's there when the Lagrangian is invariant under a spatial translation. Conservation of angular momentum is there when the Lagrangian is invariant under a rotation. So this is the standard route to conservation. In a spherical potential, we know because each component of angular momentum generates a rotation around an axis, we know that all three components of the angular momentum are conserved, and because we know that the Hamiltonian is independent, sorry, the Lagrangian is independent of time, we know that the Hamiltonian is conserved, so we immediately have four conserved quantities. We have four constraints on 6 coordinates, which leaves us with 2 degrees of freedom, and indeed the orbit lies in a plane. Again, that is, as is taught in the most elementary courses. We can always take this plane to the xy plane, and then the Hamiltonian looks like this, where there's radial momentum squared. The angular momentum around the in the plane is p phi squared, and this means that the radial, we can regard p phi because it's a conserved quantity, commutes. P phi is the same as L of z. It commutes with the Hamiltonian. So this we can regard as a parameter in a Hamiltonian that has only one spatial degree of freedom, r. That theta shouldn't be there because I've gone to the xy plane. So we have effectively a one-dimensional motion, and there's an effective potential, which is the real gravitational potential, plus the kinetic energy, which is this much. Sorry about the constant changing of notation, this is not good. Plus the tangential kinetic energy. This effective potential has a minimum at the radius of a circular orbit. And what we have is anharmonic radial oscillations. So we can show that R as a function of time is equal to a constant plus cos omega t plus another constant times cos 2 omega t plus 3 omega t and so on. So because the motion is periodic, so if you expand it in a Fourier series, you have discrete frequencies which are multiples of each other. And as the eccentricity is reduced, the frequency tends to this kappa, well, square of the frequency tends to kappa squared, which is just the double derivative of the effective potential at the bottom of the potential well, as you would expect, which could also be written like this. So this is called the epicycle frequency kappa, and this formula is quite often needed. It's immediately recoverable by remembering that kappa, as you would expect with any harmonic motion, is the double derivative of the effective potential at the radius of a circular orbit, which is the bottom of the potential well. And then having found what the radius is as a function of time by doing that one-dimensional periodic problem, you can discover what the angular coordinate is as a function of time, because it's clearly equal to this, since p phi is equal to r squared phi dot. So this becomes the integral of, with the r squareds cancelling. This is the integral dt of phi dot, which therefore is obviously delta phi. And if you work it all out, you put in what this r is as a Fourier series. You're looking at this, and you can see that phi is now going to be, it's going to have a linearly increasing part here, plus a sinusoidal series, an anharmonic oscillation here, and in the epicycle approximation, which is where you get rid of these higher harmonics and just focus on the first order term, you are looking at an epicycle. So you have a guiding center here, which goes around at a constant rate around the galactic center. That's described like this. And then you have motion in the opposite sense around an elliptical trajectory, which is described by cos omega RT in the R equation, which was on the previous slide, and a sine omega RT here with a different amplitude, which means we're moving around an ellipse. So we move around ellipse here at the radial, at the epicycle frequency, whilst cruising around here at the circular frequency. And that's a pretty decent approximation to motion in a spherical or an axisymmetric potential. All right, but let's now go to axisymmetric potentials and stop just being in the equatorial plane, symmetry plane of potential. We now recognize that the motion in the equatorial plane is kind of trivial. We can, because we've got a conserved quantity, P phi, and so we can reduce the Hamiltonian from having 3 degrees of freedom to 2 degrees of freedom, where P phi is going to play the role of a parameter in the two-dimensional Hamiltonian. And if you integrate orbits in this plane, you get things like this. So what's this? This is the Z coordinate. Here's the equatorial plane. The phi thing has been suppressed, right? So we got rid of phi, projected it out because we regarded it as trivial. We can solve for that later when we're done. We can integrate the equations of motion without thinking about phi. And what I'm showing here, 2 orbits, one in red, one in black, which have the same values of the energy and the angular momentum around the symmetry axis. So these 2 orbits are have the same constants of the classical constants of the motion coming from Noether's theorem, but they're clearly different orbits. And they are also, I think you can see these are beautiful distorted Lissajous figures, right? They clearly come from compounding, cos omega t in one direction and cos some other t in the other direction. Right? These are Lissajous figures that you see. Well, in my time, you saw on the oscilloscope. I don't know what a modern oscilloscope looks like, but you've seen it, right? Okay, so we don't have this day for you can write down a sensible squashed axisymmetric potential that might be a model of the potential of our own galaxy, and integrate the equations of motion, make a plot like this. And this was first done in the 1960s when electronic computers became easily available. But to this day, we don't have a procedure for determining what the constants. This clearly has a different constant of motion from this orbit. These 2 orbits are clearly confined by 3 constants of motion. But we only have formulae for 2 of them, except in the epicycle approximation. So the epicycle approximation again is when we go to the minimum of the effective potential. There's an effective potential, which I haven't written the full thing down in the 3-dimensional case when it says on the C. I should have done that. But there is such a thing. I go to the minimum of this thing and I expand the effective potential up to quadratic inner coordinates, delta, up to z squared and r minus r circular squared around there. And when I do that, my effective potential then looks like this, right? The first order term in the Taylor series, the zeroth term in the Taylor potential we throw away because who cares about a constant potential? The first order term vanishes because I was at the minimum of the effective potential. So the next term is this quadratic term, and this is the radius of the circular orbit. This is the actual radius, and this is our friend kappa, the radial epicycle frequency. And then obviously there's going to be a z squared term when I'm doing this in 3 dimensions, times some coefficient mu squared, which is clearly going to be a frequency, the vertical epicycle frequency. It's obvious, because these are Taylor series expansions, that is d2 phi affected by the r squared, which is these 2 bits here, and this is d2 phi affected by the z squared, which is this thing here. And so I'm clearly, my motion, if in this approximation, my motion is clearly going to be a superposition of 2 simple harmonic oscillators, and there's going to be an energy of the radial oscillator, which is this, an energy of the vertical oscillator, which is this, and that obviously is what an extension of that result is what we're seeing here. If this were all there were to it, we wouldn't have this interesting shape. We would just have a couple of rectangles, right? 2 rectangles. One was tall and the other was short. In fact, but the fact that we've got these curvy things means there's more to it than just this. Okay, now Poincaré, in the years before the First World War, gave us a very powerful tool in this context. He said, look, if I've got, which I effectively here I've got motion in the RZ plane. I've got motion in 2 spatial dimensions in phase space of 4 dimensions. So I've got something moving in 4D space. And supposing I've got 2 constants of motion, then those 2 constants of motion will confine me to a 2-dimensional subspace, a 2-dimensional manifold. The 2 constants of motion in question are, one is ordinary boring energy, and the other is the mysterious third integral, right? We've already used up our P5. We've already used up our angular momentum around the phi axis in order to reduce the problem in 3 dimensions to 2. So in this 2-dimensional plane, we've got energy, still a constant of motion. And we've got, putatively, some other constant of motion, the third integral we don't have a formula for. But anyway, so then the motion will be confined to a 2-dimensional manifold within this 4-dimensional space by these 2 constants of motion. If we now impose one other constraint arbitrarily, for example, we say let z be 0, then the star is going to be confined to a 1-dimensional space, i.e. a curve. So what we do is we integrate our orbit, and every time it passes through the plane z equals 0, we write down r in PR, or we make a dot on a PR on an r PR plot dot. And then we integrate some more, and next time it goes through the plane moving upwards, we get another point and another point and another point. And if there exists this constant of motion, these points will lie on a 1-dimensional manifold, i.e. a curve, and lo and behold, they do. So this is a Poincaré surface of section. It is a plot of a phase plane, a coordinate, and a momentum, so conjugate to that coordinate, and it's something that we can compute, and we can see that there is a constant of motion. Those 2, each one of these points is called a consequent in this plane, and those 2 sets of consequents derive from the 2 orbits that I just showed you before. Okay. Now, another thing that you can do is store the time series R of t. So we've been integrating the equations of motion. We've got R as a function of time. We can store it. We've got Z as a function of time, and we can store it. And then we can Fourier transform these time series. And when we do that, we discover that they're quasi-periodic. What does that mean? That means that the spectrum consists of only discrete frequencies, not a continuum. We're doing the Fourier transform of a continuous function of time, but what drops out is not a continuous spectrum, not a continuous. Only certain sinusoids occur, and these sinusoids that do occur can all be written as linear combinations, integer linear combinations with just 2 frequencies. And this is exactly, so this is, and this plot here is very instructive. It is just, if I took the Fourier transform of these 2 time series, one of them is in red, the other is in black. This is the logarithm of the amplitude of the Fourier term. This is frequency along here. One of these is radial, the other is vertical. It hardly matters. The point is that it is all discrete. Okay, so that tells you that these time series you get by doing this integration, when there is the constant of the motion, even though you don't know what it is, makes the time series quasi-periodic. So a periodic function, just to remind you, is one where the number of frequencies is equal to the number of degrees of freedom. So in one dimension with time, that means that there's only one frequency. So if I have a Fourier series with only one frequency, I have something which is periodic. It won't necessarily be sinusoidal, but it will repeat itself. Quasi-periodic means that there's more frequencies, but they're still distinct than there are spatial dimensions. So a crystal has three frequencies: the frequency associated with the x direction, the y direction, z direction, whatever your basis, what do you call it? Anyway, your lattice vectors are. A quasi-crystal has maybe four frequencies, etc. So we're dealing with quasi-periodic functions, very important concept. In astronomy, quasi-periodic is often used in a looser sense, meaning sort of vaguely periodic. This is the very precise sense. There's nothing vague about this. Okay, now, action angle coordinates. We've just got time to convey, I think, this important idea. So, what's the idea is, now we've got a problem where we've got two constants of motion in a two-dimensional system. So we've got two constants of motion in a four-dimensional phase space. Aha. Why don't we make those two constants of motion the momentum of the system of canonical coordinates? Then my equations of motion will be trivial, because I will find that the rate of change of one of my momenta, I'm going to call these momenta J1 and J2. The rate of change of one of these momenta is going to be nothing, because it's a constant motion, which means the Hamiltonian will not depend on the corresponding canonically conjugate variable, which I'm going to call the angle theta I. And consequently, the rate of change of the angle theta I, which is the gradient of the Hamiltonian with respect to J1, because that's Hamilton's equation in motion, is going to be a constant, because this thing doesn't depend on the thetas, which are changing in time. It depends only on the j's, which are not. So the equation of motion, or the motion of theta, is going to be linear. So the angle, this gets to be called an angle variable for reasons that will become apparent. So this variable, it increases linearly in time at a rate which is determined by this gradient of the Hamiltonian with respect to the actions. And the momenta are going to be constant. So dynamics, if we can embed in a system of canonical coordinates the constants of motion we found, the equations of motion will be absolute, the equations of dynamics will be absolutely trivial. One coordinate, or the momentum, will stay constant, and the coordinates, the angle variables, will increase linearly in time at a known rate. Now, every function, let me call it J, but now I'm just saying every function, Hamiltonian, angular momentum, you write down some stupid function on phase space. This stupid function on phase space generates a trajectory through phase space by the following principle: that the rate of change of a phase space coordinate with respect to parameter of psi that tells you how far down this transformation you are is by definition the Poisson bracket of that coordinate and this function you just wrote down. So you write down a function, we can evaluate this Poisson bracket for whatever coordinate we desire, and therefore we can integrate this equation of motion and get W as a function of a psi, that's a trajectory through phase space. So your function on phase space generates a trajectory through phase space because the Poisson bracket exists. Now, let's apply this principle to W is theta j, we're going to discover that the rate of change of j with respect to psi is the Poisson bracket of j with respect to a with sorry of excuse me yeah. Yes, sorry, I'm good. I'm going to put theta, I'm going to put j into here. So the rate of change of j, which is a coordinate, because we've established, sorry, yes, right, okay, I'm going to put the rate of change of j with respect to psi is equal to j comma j, which is nothing. And the rate of change of theta with respect to another psi is just what tells me how far down the curve I am, is going to be theta comma j, which is going to be 1 when k is I and nothing otherwise. So what does that tell me? That tells me that that tells me that lost my thread slightly. This is a very subtle. There is something slightly unclear here. Right. So I am not claiming. Yeah. Right. We have defined j as a function on phase space. Right. We intuited it exists. We can't write it down, but it is a function on phase space. It's a constant of motion. And we've hypothesized that we can complement it with two canonically conjugate variables we're calling the angle variables. If we can do that, then it's clear that the rate of change of the j's will be nothing and the thetas will increase linearly. Now, any old function, nothing special, generates a flow through phase space by this rule. So let's ask what happens, what j does to what the function, what kind of curve j generates. And the answer is it causes theta to increase. It causes its own theta to increase at unit rate, and all the other coordinates stay constant. So the function j is drawing a curve, which is a curve of increasing its own conjugate angle, and the other angle staying put. That's what I'm trying to say. And actions are particular constants of motion which allow these curves to close on themselves. So you can go on integrating this equation of motion for theta. You can go on drawing this curve for theta until you're blue in the face, right? You can just integrate. And if you took any old function on any old constant of motion, this curve would just wind its way endlessly through phase space. We don't want that. We want to construct a coordinate system, a useful coordinate system, on which the thetas, the conjugate variables, tell us where we are on the surface of constant j. So I want this curve to go on and close on itself. And that property makes a constant of motion an action. They are an elite actions. They are a master class amongst all constants of motion. They don't grow on trees. You'll find they're not unique, right? But they're absolute aristocrats. And what makes them special is that they draw these curves that close on themselves. And then these curves are going to form a nice network coherently, which we can use as a coordinate system to tell us where we are on the surface of constant j. So that when somebody tells you that this star is at location theta theta jj, you will be able to pinpoint the exact place in phase space where it is. You'll find the surface of constant j with the numbers jj, and you'll integrate your equations, these equations, so that one theta increases by the approved amount, and then the other theta increases by the approved amount, and you'll be there. Okay, now we can always rescale if we found curves which close on themselves. We can always rescale the j's so that they close on themselves after theta is increased by 2 pi. I haven't written down the generating function for the canonical transformation from a set of coordinates where it does to where it doesn't close after 2 pi, but you'll find that in the draft book. It's trivial. And so it's a convention that we do that. And that's why the thetas are called angle variables, because when you increment a theta by 2 pi, you come back to the same place. There's a countable infinity of angle action coordinates. I told you they were aristocrats, but not unique. But they're all related to each other by a generating function of this type. So this is a generating function which depends on a new coordinate. Remember, generating functions for canonical transformations always depend on a new, some new thing and some old thing. So the generating function we're choosing here depends on a new angle variable and an old action. And it's going to be a new angle variable dotted into a matrix. This matrix, we'll see, has to have integer entries times old action. We'll see. Sorry, it's demonstrated in the book. It's a very easy exercise to convince yourself that the new, if that being so, the new if you take this generating function and calculate what the new angles are in, sorry, what the old, yeah. So if I do the derivative of this with respect to j, I will get theta, the old angle variable, is equal to this, is equal to d by dj of theta prime m j is equal to theta prime dot m. Right? You might want to put a transpose on this or something if you're fussy. And what I want is that when one of these increments by 2 pi, these all increment by a multiple of 2 pi, 0 or 2 pi or 4 pi or whatever, right? Otherwise, we won't have the magic property, and vice versa, and that will be guaranteed if m is the elements of m are integers. So the action's not quite unique, but they are unique-ish. All right, we're pretty much ready to stop. Let me just introduce the next topic, but only introduce it. Basically, in a slightly sketchy way that I think Matthew complains about, I have introduced, I've established all these surfaces of constant j, on which orbits, to which orbits are confined, are topologically speaking tori. We were doing motion in a 4-dimensional phase space. We had 2 constants of motion. Those each pair of constants of motion defined 2 torus. And these angle variables tell you how far around you are in the torus in either the small dimension or the big dimension. If we are dealing with stars in our full 3-dimensional galaxy, then we're talking about motion. Each orbit is a 3 torus, which is analogous to a cube, like the room, or cuboid like the room, with opposite points on the walls identified, points on the ceiling and the floor identified, points on the wall identified. so that if you pass from the floor up to the ceiling, you reappear on the floor just right below. So that's the basic structure. So a galaxy I want to regard as being assembled out of a large number of these three-dimensional tori. And they're going to be the stuff of phase space. The natural, how do we measure these? How do we quantify one of these tori? Well, Poincaré showed that if you do the integral PdQ around a closed path, the number you get out is independent of which canonical coordinates you use. So if P and Q is one system of canonical units and coordinates, and big P and big Q are another, these two integrals around closed paths, any closed paths in phase space, are the same. So we can now do this on particular closed paths on our orbital tori if we make Pj and Q theta, then the j, of course, and we move around on the surface of constant j, then we can take the j outside the integral, and we'll be left with j times the integral dq all the way around, 2 pi. Then we'll find that this integral, this Poincaré invariant, is equal to 2 pi ji. So that's what the actions are. They're sort of measures of how far around, how big the torus is. What's its girth? Height girth. Now, this is very important. Any function f of w of angles, any function on phase space can be Fourier expanded in the angles. In other words, we can write any function on phase space, i.e., because we've established that theta and j are coordinates, can be expanded as some coefficients that obviously depend on which torus we're expanding on, times e to the I k theta, where the k's, this is a three-dimensional vector with integer components. This is just saying that f is a periodic function of the angles, and therefore, when you Fourier expand it, you get any discrete frequencies. And when we substitute in that the time dependence, the trivial time dependence of the angle variables under the equations of motion that we already established, you find that a phase space coordinate is a function of time and actions, while actions are constant along our orbit, is simply a series of constants times e to the I k dot omega t. In other words, we recover the quasi-periodic property of phase space coordinates when you integrate an equation of motion. So that quasi-periodic motion, which you can convince yourself of by integrating the equations of Fourier, decomposing them, is telling you that there are actions. This orbit is on a torus. It can be quantified by actions. You don't know quite what the torus is. We don't know what the actions are, but you know they exist. And we'll carry that idea forward tomorrow. I'll leave it there.